All right, so
Okay.
please.
Thank you very much. Thanks for the invitation and for rescheduling. So it's a pleasure to be here. Yeah, feel free to write questions in the chat or just jump in and interrupt. So let me just start by a general introduction. Okay, so Lagrangian fibrations are the natural higher dimensional generalization of elliptic K3s. And in fact, in the same way, elliptic K3s occupy a crucial role in the theory. Similarly, they have been used extensively to study, construct, attempt classification, compact hyperkähler manifolds. So in this talk by hyperkähler, in fact, it will mean compact hyperkähler mostly. And in particular, sometimes it will be irreducible holomorphic symplectic, but I'll try to sort of mention when this is the case. And so maybe before I go on, I should say, what is a Lagrangian fibration? So Lagrangian fibration is a proper surjective morphism with connected fibers from M, F to B. So where here M is Kähler, not necessarily compact, but has a holomorphic symplectic form. And B is normal, quasi-projective, doesn't have to be quasi, well, normal, and the general fiber of F is Lagrangian. Okay, so when I say a quasi-projective Lagrangian fibration, I mean that the morphism F is quasi-projective. And here I ask that the morphism is proper, or when I say a projective Lagrangian fibration, I mean the morphism is projective. I'm not asking that M or B are necessarily projective. Anyways, I'll maybe say that later. And so by Matsushita, if M is irreducible holomorphic symplectic, and so maybe this means that it's compact Kähler, simply connected, and the space of holomorphic two forms is generated by a symplectic form. Okay. And if F from M to Y is a proper surjective morphism with connected fibers, then there are only two possibilities. Either the dimension of Y is equal to the dimension of M, in which case F is birational. And so it's either, if Y is singular, it's a symplectic resolution, or if Y is smooth, then it's an isomorphism. Or F is a Lagrangian fibration. So there is this dichotomy, which for K3 surfaces is sort of pretty trivial, but in the case of the higher dimensional hyperkähler manifolds, it's kind of a remarkable fact. And so this is one of the reasons why symplectic resolutions on one side and Lagrangian fibrations on the other side are kind of the basic tools to study these things. Okay, and so maybe I should mention that in a Lagrangian fibration here, so if by result of Huang, if in this case, if in the Lagrangian fibration case, if Y is smooth, then Y is isomorphic to Pn, where N
Yes,
is.
we have a question in the chat.
Oh, yeah.
Is it possible to recall what Lagrangian means? Or
Oh, yeah. So Lagrangian, so if I have a symplectic vector space V, Lagrangian subspace means, so symplectic is a non-degenerate alternating form, two form. And so the, for that to exist, V has to be even dimensional, and a Lagrangian subspace just means that that W is isotropic for the symplectic form. W isotropic. And meaning that the symplectic form vanishes identically on when I plug in vectors of W, and Lagrangian means that the dimension of W is half the dimension of V. And so a typical example, if I have M compact hyperkähler manifold, and I have inside M of dimension 2n, and I have a projective n space, then because Pn has no holomorphic forms, the restriction of the symplectic form to Pn is identically 0. And so what this means is that the tangent bundle of Pn is in every point, the tangent space is at every point is a Lagrangian subspace. Does that answer your question? And so maybe the sort of trivial example is a curve inside a K3. Okay, good. Again, this is for just because curves have no holomorphic two forms. And so, okay.
In the chat, we got awesome, thanks.
Okay, good. Okay, so what is the main question that I want to address today? So given, and I'll use this notation, mu to u, pi u, a Lagrangian fibration, and now compared to what I was asking earlier, I want mu and u to be quasi-projective. So mu is not just Kähler, but quasi-projective. And suppose that this is a Lagrangian fibration, the question in when does there exist a hyperkähler compactification of pi u. And a little appropriately, what I mean by this, I mean compactification of mu with a morphism to a compactification of u, such that this thing is hyperkähler. So in this case, projective, and so projective hyperkähler with a holomorphic two form, a symplectic form. Okay, and there are obstructions to the existence of such a compactification. So I'm going to talk compactification of a morphism, where I'm talking about compactification of top and bottom, and here usually, in fact, we'll look at sort of, maybe let me just say, most likely we're going to be looking at an open subset inside Pn. This is going to be, but not necessarily. Okay, and so the goal today is to give a framework to answer this question. And so I'm going to discuss a kind of general method that is, works in some cases, and I'll discuss which cases that it works. And one of the reason is because that is a sort of interesting question, but also it happens sometimes that people come to me and ask me, I have this Lagrangian fibration. Can you compactify this? What can you do? How do you do it? And where do I start? And so I'm kind of giving a general answer to some of these questions. Okay. And so before I do that, I should first sort of say what are sources of these Lagrangian fibrations like this, whose total space are quasi-projective. Okay, and sort of there are many natural examples that come from geometry. And there are two main techniques given a family of, say, abelian varieties. There are two main techniques to construct holomorphic two forms on the total space. And so, so here, holomorphic symplectic forms on families of abelian varieties. And so the first technique is due to Donaghy-Markman. And it's the so-called cubic condition, which I'm now going to be briefly recalling. So I suppose that mu to pi u is a family of polarized abelian varieties. I think in their paper they asked for it to be principally polarized, but in fact it's any polarization that it happens in family will do. Okay, so first of all, I should say that given a Lagrangian fibration, a necessary condition for the existence of a holomorphic symplectic form with respect to which the fibration is Lagrangian is an isomorphism between the vertical tangent sheaf or bundle, because I'm looking at a smooth thing, and the cotangent bundle of the base. And sort of this is a little lemma that you can prove. If there is a symplectic form, then there is such an isomorphism. Okay, and let me call this, following their notation, by V for vertical. And so the Donaghy-Markman cubic condition is given such an isomorphism from V dual now to the tangent bundle of the base, then phi comes from a holomorphic two form, symplectic form, on the total space, if and only if, in fact, it's the following thing happens. So the sort of period mapping associated to the family of abelian varieties to the moduli space of principally polarized abelian varieties of the correct dimension induces a map from the tangent bundle, just the period map. I'm just locally looking at the tangent, tangent map to the period map is induces a map to sim2 of V. Okay, and this is where you need the polarization. And so the claim is that this isomorphism comes from a holomorphic symplectic form if the composition of this map, so here maybe the isomorphism is here, this is coming from if and only if the composition of this map from this to sim2 of V comes from a section in U sim3 of this tangent bundle. Okay, anyways, I'm not gonna actually use this very much, so maybe I should not have spent that much time, but the upshot is that this is a very concrete way of checking and it works well on the smooth locus on smooth families. So I'm here, I was assuming that is a family of abelian variety, so the morphism is smooth. And it gives many geometric examples. And for example, any families of pick, the relative pick 0 for a family of Lagrangian submanifolds on a holomorphic symplectic manifold have a holomorphic symplectic form. So and sort of one example is maybe the sort of intermediate Jacobian fibration. Associated to the family of hyperplane sections of a cubic fourfold. Okay, so just giving, or for example, even the pick 0 of the relative pick 0 of a linear system of curves on a K3 surface. Maybe before that, if C is a K3 surface, and I have the universal family, and then pick 0. Oopsie, over here. Okay, and so what is the drawback? The drawback is it's not easy to check the closeness condition, and it's not easy to extend. It's hard to extend to singular fibers and to check that the form is closed. Okay, so an alternative way of, or maybe I should say not alternative, but complementary, is what I want to call a cyclotheoretic condition, cyclotheoretic symplectic form. And which I would mostly attribute to Voisin. And so I'm maybe just going to give a couple examples without really telling you. It's more a philosophy, I would say. And so let me give 2 examples, and in particular, the sort of the good thing about this way of looking at the homomorphic symplectic form is that it kind of solves these 2 issues. And so the sort of upshot of this discussion, after I tell you what I mean by cyclotheoretic holomorphic symplectic form, is that using Denagi-Markman, you can find lots of examples, and then using this, you can kind of sort of try to extend it. Okay, so what do I mean by this? So let me give you 2 examples. And sort of, you've probably seen me give the sort of this example before. And so let X a cubic fourfold and gamma V inside V cross X over V. So V, a quasi-projective smooth variety, and I have a family of curves on X parametrized by V. Okay, and so what this tells me is that for any say, I don't know, Z, smooth projective compactification of V, I get a cycle in the Chow group of Z cross V just by closing whatever thing I have here, just by closing this cycle. And so maybe let me write it gamma, and the correspondence of the cycle. Sorry, this is Z cross X. I'm closing, this is inside Z cross X. I'm closing the cycle there. And so this gives a map from H4 of X to H2 of Z, which is a morphism of Hus structures. And in particular, H31 of X goes to H20. This shifts the degree by 1, 1. And so the observation here is that because if I have a cycle on one birational model, I have a cycle on any birational model, then I don't care what compactification of my base I pick, and it will have a holomorphic 2 form. Of course, this form could be 0, and sometimes it is 0, and so then you have to work to get that this holomorphic 2 form is actually non-degenerate. But the advantage is that if you know that the symplectic, that this form is non-zero, then it's automatically closed, because the holomorphic 2 form on a smooth projective variety is closed by the Hodge theorem, Hodge decomposition. So the advantage of this is that, first of all, I don't need to actually ask for an effective cycle here. I could also just look for any element in the Chow group. And so so this is what I'm saying, is that the advantage of looking at the forms in this way is just that it gives a lot of leeway to extend symplectic forms. Are there any questions about this? And so maybe the remark is that when V is a quasi-projective Lagrangian fibration, then you get a holomorphic 2 form in appropriate circumstances on any smooth projective compactification M of mu, and the Lagrangian fibration structure gives you a way of checking if the form is non-degenerate. So in here, I'm saying this V was just a random base of a family of curves on X. And so I just get a random 2 form here, holomorphic 2 form. And of course, I need to know something about the family to know if this form is non-degenerate or not. And so I'm saying that when I have holomorphic symplectic forms on Lagrangian fibrations, I have concrete ways of checking if the form is degenerate or not. Okay, and so the other remark that I wanted to make is that, if I have a symplectic form that is given in this way, then it's I just would like to compare this extension result. I mean, this is more a philosophy than extension, but to classical extension theorems of holomorphic forms. So I'm thinking about, I don't know, Griffiths, Flenner, even more recently, Kebekus-Schnell. And sort of, this just indicates that in general, it's hard to know if I have a singular compactification of something with a holomorphic form, it's hard to know when this holomorphic form extends to a resolution. And, you know, usually that's not the case. But if in this context, the symplectic form is given in this way, then you kind of have this automatic extension, which indicates that the sort of cases where you have this property is kind of restrictive already. Any questions about this? Okay, so let me give you Theorem 1. This is work in progress. I mean, this theorem is written, but I'll say maybe a little bit at the end of kind of further directions. So now B is normal projective. And U is an open subset, non-empty. And I suppose that MU to U is a Lagrangian fibration. And here MU is a smooth quasi-projective, and with holomorphic form, holomorphic symplectic form sigma U. Okay, so then suppose that the codimension of the complement of B and U, of U and B, is greater or equal to 2, then the conclusion is the following. There exist, sorry, no, I need another assumption. Suppose these two conditions hold, and that there exist an M tilde, MU, smooth projective compactification with a holomorphic 2 form, sigma tilde extending sigma U. And so the whole discussion about the cyclotheoretic holomorphic symplectic form is an indication to say that sort of this extension property that I'm assuming here is often satisfied in geometric settings. Maybe it was not clear, but that was the kind of where I was going. Okay, then, oops. There exist M to B pi compactification of pi U, meaning that I have a commutative diagram like this, compactification of pi U, where the total space is Q factorial terminal symplectic. Okay, so I'm going to comment maybe on that in a second. And moreover, the following are equivalent. One M is smooth, 2 M is birational to hypercalomanifold. and 3, M is smoothable by a flat deformation. Okay, so let me just keep this theorem on and maybe comment on the assumption. Before I go ahead. What do I want to say? Okay, maybe actually let me make a remark. Okay, so a remark, a similar, the same kind of ideas was used in a paper I have online to show that if X is any smooth cubic fourfold, the intermediate Jacobian flibration has a hyperkähler compactification, Lagrangian fibered hyperkähler compactification. So, and this is a case, so this is an example of a case when, in fact, the upshot that you get is you can check smoothness. And so sort of a good thing about this theorem is that it's pretty general, and sort of the assumptions are satisfied in cell settings, and I give some examples in a little bit, but it's first of all very inexplicit. That I'm just claiming the existence of compactification with those properties without actually telling you how it looks like, and also in general, it's not easy to check either of these conditions. So maybe I'll sketch a proof of this theorem later, but maybe I would like to give some applications of this. But in sort of, let me just give you an idea of how you apply this kind of theorem and the smoothness in this to get a hyperkähler compactification of the intermediate Jacobian formation of any smooth cubic fourfold. And here I should remark, of course, that it was known by LSV such a compactification exists for general X. And so in the sketch of proof that I'm going to give you, just to show how to use a theorem like this, I in fact use this, and maybe I'll the fact that I know the compactification exists for general X, and so so the how do you prove such a thing using using this theorem? So if I have a family of cubic fourfolds, then actually maybe let's say before I do that, so by the cyclotheoretic approach to actually, symplectic form, given X, any smooth cubic fourfold, and given the intermediate Jacobian fibration over the smooth locus of hyperplane sections, then the assumptions of the theorem are satisfied. And in fact, it was already known by Donaghy-Markman that you can compactify kind of in codimension 2, adding the locus of nodal cubic threefolds. And so by the theorem 1, so assumptions of theorem 1 are satisfied. And this gives compactification that a priori has only q factorial and terminal singularities. But using the fact that that the result is known, meaning that you can compactify to a hyperkähler, result is known for general X, you deduce using the equivalence of 3 and 1, meaning that this is smoothable if and only if it's smooth, you deduce that that J bar is actually smooth. So in this sort of, I'm actually using the fact that I know the result for general X to know that this compactification that I find is smoothable, and hence by the equivalence above that in fact it's smooth. I should write a remark that in fact, but I am not going to prove it using similar ideas. You can actually reprove the result of LSB without actually assuming it. For that, you need another kind of a family of cubic fourfolds. Maybe if people have questions, I'm happy to answer and explain the proof, but otherwise I want to move forward. So this is just an example where sort of, you actually get a conclusion, a non-trivial conclusion out of this theorem. Of course, in general, it's not easy to check either of these assumptions. But I would also like to make the case that for many purposes, having something with q factorial terminal symplectic singularities is also good enough. And so okay, so let me maybe maybe mention a few applications, other applications. And so one is that is in progress. So following Markman, if M is, or maybe X now is hyperkähler, and Z is a Lagrangian submanifold, then you would try to construct a pick 0 of deformations of Lagrangian fibrations, Lagrangian submanifolds over the Hilbert scheme, the appropriate Hilbert schemes of Lagrangian submanifolds in X. And So this is in progress. I mean, of course, if you don't, a drawback of this theorem is that if you don't already have something that you know is a hypercal manifold, it's hard to get smoothness in general. And so from the point of view of getting new examples, it's not necessarily easy, because you kind of already need to assume that either you check smoothness by hand, but it's not easy, or you already know that it's birational to something that is already hyperkähler, in which case they have to be the information equivalent, so you don't really get new examples. Other examples is family of relative prim varieties. And again, I don't want to enter the details, but here the sort of you get things that most usually what you get is things that are Q factorial terminal symplectic without symplectic resolution, non-smooth examples. But in fact, a good thing about this is you don't get smooth examples, but you get you may get irreducible holomorphic symplectic varieties. So maybe in a joint work with a bunch of people, I don't want to forget their names. Bracchi, Camere, Annalisa Grossi, Laura Pertusi, and myself and Sasha Viktorova give examples of singular irreducible holomorphic symplectic varieties. And this, so maybe I'm not going to say the definition, but recently, thanks to the work of many people, Greg Kepicus Pertinel and sort of many other people, there's a singular version of the Bogot-Molov decomposition theorem, and sort of these families of relative prim varieties should give conjecturally, I mean, the examples that we're looking at, examples of these building blocks. And in the same way, in the smooth case, you look for these building blocks. Similarly, for the singular cases, not many examples were known. And here, I should say that this family of relative prim varieties, the sort of people who started the theory were Markushevich and Tikhomirov. And then Arparello, Ferretti, and Sacca, and myself. And then there was the sort of, the theory was, and so we constructed many examples coming from K3 to a quotient of a K3 by an anti-symplectic involutions. And then there are other sort of similar examples constructed following these two things, constructed by Matteini and Sewon and Chen. Okay, so maybe before, and then I'm going to give another application of this theorem, which is which will be the Theorem 2 of this talk. But before I do so, let me make an important remark. Is that you cannot, in general, remove the could-I-mention 2 assumption. And the counterexample is the following. So suppose I start with a Lagrangian fibration over P2, and I take a non-trivial Cremona transformation from P2 to P2, and suppose U is the largest open set where G is an isomorphism, and so I have G of U here, and over U I can pull back the restriction of the fibration to U, and I call this map pull back of pi restricted to U. And so the claim here is that, so this, of course, the complement, of course, has codimension 1. And the claim is that there exists no compactification. There exists no hyperkähler compactification of this pullback morphism, at least without changing the base. Of course, if I change the base and I go back to the previous one, then I already had it. So there's nothing here completing the diagram. I can't have it. Okay, so this is just to say that in general, that the sort of, I'm not saying it never happens, but of course, you know, you have to be careful about codimension 1. Okay, any questions about this? So maybe since I have 10 minutes left, instead of sketching a proof of this, let me give you sort of another application of this circle of ideas that is a case where you can check smoothness without actually having something that is very rational to what you constructed that is hyperkähler. So another application. Theorem 2. Let F from X to B be a Lagrangian fibration with integral fibers. And X is projective hyperkähler. Okay, I need that F is a projective morphism. Okay, and let A from A0 to B be the relative Albanese fibration. Of F. This exists by result of Markushevich and Arinkin-Fedorov. I'm going to say what it is in a second. Then for any P from P0 to B, so A0 torsor over B. So maybe actually I should say, before going ahead, what I should say is what the Albanese fibration is. It's a abelian group scheme. In particular, it has a section which acts on X. And so on the smooth locus, it's just the same family of abelian varieties, except that it has a section. And then on the singular locus, you're adding degeneration of abelian varieties. But this, so here this is not a projective morphism. This is the fibers of this morphism will not be compact because it's a group scheme, and with sort of non-compact fibers. When the fibers of X are singular, then the fibers of this will be just non-compact groups. Okay, and so then for any A0 torsor, the statement is that there exists Y to be smooth projective hyperkähler compactification of this torsor. Oh, here, I want P0 to be quasi-projective. So it's not just any torsor, but I want the total space of this torsor to be quasi-projective. There exists Y to V smooth projective compactification, and it has a property, eta locally on the base, it's isomorphic to X over B. Okay, so maybe this is kind of abstract, but in practice, in particular, what I'm saying is that if X to B does not have a section, then there exists a hyperkähler with a section, Lagrangian fibration with a section, that is eta locally isomorphic to the thing I started with. Okay, so this, first of all, maybe I should say that this answers a question by Wazan, but also by Seiwan, an older question by Seiwan, of this existence of, given a hyperkähler with a Lagrangian fibration, does there exist one with a section that is sort of, that compactifies the family of abelian varieties with a section that is associated to the one you started with. Okay, so this, but in fact, it's more because it kind of shows the existence of compactification for any torsor over this A0 over B. Okay, so let me give a few remarks. Well, first of all, for K3, it's classical. I mean, you can always take the pick 0 of an elliptic K3 and it's going to have a section. And just because you're in the surface case, you know that the pick 0 has a sort of symplectic compactification, if you want. So it's a kind of extension of that kind of result. And here I'm not asking the fibers to be principally polarized, but if the fibers were principally polarized, then this fibration with a section would be the same as a compactification of the pick 0 of the family. And okay, so these are a couple remarks. Then so that was 1, 2. The modulo some technical assumptions, it's expected that the rational Hodge structure of the two fibrations is the same. So, I mean, basically, it's true. There's just one technical assumption that I haven't verified, but it's expected to hold true. And so then you can start, you know, probably these two things are deformation equivalent, but there are many questions you can ask. Are they derived equivalent? And sort of there's a whole, like, you know, platter of questions that you can ask starting from here. And the other thing I should say is that you cannot, in general, remove the assumption on the integral fibers. And so if you want the smoothness. So, so in fact, there are many examples that you can construct of Lagrangian fibration with reducible fibers, non-integral fibers, whose relative Albanese does not admit smooth hyperkähler compactification. So it's sort of interesting to. On the other hand, in some cases there is. So even here, it's just a sort of interesting thing to understand if there are other conditions. You know, if you drop that assumptions, are there other conditions that you can put on the original fibration you start with in order to achieve smoothness? And so the last thing I wanted to say, and sort of this is part of the paper that I haven't yet written, is there are many variations that you can do on this theorem. And so, for example, you could say it has integral fibers only in codimension 1. Or instead of taking compactifications of the torsors of A, I take compactification of families of things that are kind of isogynous to A0. So instead of having something that is locally isomorphic, I just have a finite morphism. And so then with all these variations, what you get, using sort of the techniques similar to Theorem 2, you get Q factorial terminal symplectic compactification. So for example, if I have F to be, say integral fibers, but integral fibers in codimension 1, then there exists a Q factorial terminal symplectic compactification of pic 0. This is the case where I'm compactifying something that fiber-wise, it's not isomorphic, but has a finite morphism from the original fibration. And so, again, in this case, in general, for the moment, I can only get Q factorial and not smoothness, the way I could have actually smoothness in this case. So I guess I had prepared in my notes sketches of proofs, but I guess I have 1 minute left, so I can end here, and then people can ask questions if they're interested in.
So maybe we should I'll stop the recording if that's okay, so people are free to ask questions.